In this work, we propose our ImTooth, a neural implicit approach for dental augmented reality. The combination of augmented reality, AR, and dentistry is an important trend in current research. Doctors can use wearable AR devices such as AR glasses for preoperative practice and intraoperative assistance. The two most important components of dental augmented reality are tooth reconstruction and registration. Existing solutions require the use of expensive intraoral 3D scanners to digitally reconstruct the oral cavity and requires prefixed man-made markers for registration. These methods increase the cost of treatment and increase the difficulty of operation. Our goal is to use wearable AR glasses, such as HoloLens 2, as the only sensor, combined with cloud processing, to integrate reconstruction and registration, reduce reconstruction costs, and facilitate use. In recent years, 3D reconstruction and registration based on neural implicit representation has gradually shown potential, which has great advantages over traditional methods in reconstructing weakly textured regions and ensuring multi-view consistency. We hope to combine such methods with dental augmented reality. Our proposed method can use the data captured by AR glasses to reconstruct the teeth model with neural implicit representation. With the help of trained implicit model, we can perform pose registration for different potential applications, such as tooth bracket placement navigation in orthodontics. Our system consists of two modules, reconstruction module and registration module. In the reconstruction module, the RGBD data collected by HoloLens 2 are used as input. We use volume rendering to simultaneously reconstruct the color, geometry, and edge information of the implicit model and optimize pose. In the registration module, the geometry and edge information of the reconstructed model are used to optimize the pose of the query image. Our network structure is shown in the lower left, is a very shallow MLP. In order to better reconstruct the tooth model, we use a coarse-to-fine reconstruction method. In the coarse level, we align the model with real scale, then perform keyframe and non-keyframe pose optimization at different stages to obtain a rough tooth reconstruction model. To recover the detailed information of the teeth, at fine level, we continuously subdivide the coarse voxels and then prune the redundant voxels to fine-tune the implicit representation. For registration, the RGB images of plaster model and the real teeth are in different domains. It is hard to find visual correspondences between different domains, which makes registration more unstable. Therefore, we want to use contour information to assist the registration. It can be seen that the edge maps of different domain images can show consistent visual information, which can be used to assist pose registration. Our optimization loss consists of four components. The first is photometric loss, which minimizes the difference between the observed color and rendered color. And binary cross-entropy loss of edge map, which is used to model the edge information. The iconal loss is used to constrain the radiance filed. At last, the full depth loss is used to model the geometry structure of the tooth model. For the reconstruction results, we compare our method with traditional method, ColMap, and recent implicit methods, Noose and VoxSurf. As can be seen from the picture at the top, we can achieve comparable reconstruction performance without pre-process. And our method is able to recover more details of the tooth model. From the table, we show some quantitative results for comparison. We can achieve comparable performance with less network parameters and get rid of the need of pre-process. We also show the reconstructed voxels and mesh in the right. We show some rendering results of RGB and edge map of different views, and we can see that our method is able to maintain the consistency of edge map in the 3D space. For registration module, we compare the quantitative results with HLOC and ICP in the top table, and show the translation and rotation error in the figures. As can be seen, ImTooth can achieve the best results for the purpose of registration. Besides, combining depth and edge information can get better registration results than only use depth information. We show some visual results of iterative pose optimization. We overlay the 3D model on the query image with estimated pose of different iterations. With 300 iterations, we can obtain a good registration results. ImTooth-based dental brackets guidance system consists 4 modules. The reconstruction module is used to reconstruct the tooth model based on neural implicit representation. The bracket placement module is used to determine the position of the bracket on the reconstructed model. Then, the registration module is used to align the actual tooth image with the reconstructed model. At last, the augmented reality module performs virtual real fusion display according to the estimated position. We show some AR demo for virtual bracket position and AR bracker guidance from third-person view and AR view. Thanks for listening.